All right, at this point, we're ready to jump into talk about integration. Integration is going to be chapter 4. And where we're going to start is, let's say that we have a function f, and f is going to be a function of a single variable. Say it takes variables in the interval from a to b, so it's going to have all real inputs, and it's going to output a function into the complex plane. So you could think of something like whatever, e to the it, or whatever. And so you have a function whose inputs are real numbers, the outputs are complex numbers. And in that case, you can define the integral, and this would be the integral of just f of t, where t goes from a to b. This is going to be the integral of the real part of f plus the imaginary part of f. So if f were to be, say, u of t plus iv of t, this would be the integral of u from a to b. So again, that's just the real part plus I times the integral of the imaginary part. And everything is perfectly straightforward. There's no complications. That's how we define a function if its inputs are real numbers, even if the outputs are complex numbers. So nothing interesting or different so far. But what do we do if we have a general complex function? So let's say we have f mapping G to C. Okay, so G is some, say, open connected region in the complex plane. And what I want to do is I want to define the integral of f. And what we have to do is, it turns out that the most natural way to do this is to use path integrals. And path integrals are a topic that you undoubtedly have seen before in Calc 3. So what we're going to do is we're going to define the integral of f over gamma. Remember that we're abusing notation slightly. We use gamma to denote not just the curve itself, so the geometric object, but also the equation that expresses that curve. And so the integral over this curve gamma, and we might write it as the integral of f over gamma. We might write it as the integral of f of z dz, where the integral is over gamma. But this is going to be defined as the integral, let's say gamma. So let's say gamma parameterizes this curve, and gamma has inputs from a to b. Then this is going to be defined as the integral from a to b of f of gamma of t times gamma prime of t dt. Okay, so that's how that line integral is going to be defined. So I think at this point, it's worth just, before we do anything else, let's just do some examples. I want to get used to this definition. And let's see a few things that will come up kind of naturally. So let's start by evaluating the integral of f where over gamma, where I want to evaluate the curve f of z is z squared over 3 paths. Okay, so over 3 paths from, say, the origin to the 1, 1, to the complex number 1 plus I. And I want to do it over 3 paths. So the first path is just going to be the straight line from the origin to the point 1 plus I. So that'll be gamma 1. Okay, so gamma 1 is going to be t plus it, as t goes from 0 to 1. Gamma 2 is going to be along the parabola y equals x squared. That also goes through the point 0, 0, and 1, 1. In the parameterization there is y equals x squared. So that means that whatever your x is, y is going to be square that. And it's going to go from 0 to 1. And let's do a third. Let's actually make that a color, just so this is a little easier to follow. Let's color that red. And then likewise, let's call gamma 2. Let's make that red. Hopefully that gets everything there. Okay. And then let's do gamma 3 is purple. So gamma 3 is going to be the path along the horizontal axis. Let me try this a little with a little bit better color here so we can see it. Let's make it green. This is going to be along the horizontal axis. So from 0, 0 to 1, 0. And then straight up. So straight over and then straight up. So gamma 3 is actually going to be 2 curves. And so we can call those gamma 3. And so I guess we might as well call these gamma 3 and gamma 4. And then gamma is going to be what I'm going to call the union of these two curves, which is really, so gamma itself is not a smooth curve, but it's piecewise smooth, meaning that it consists of two smooth pieces. And gamma 4 starts where gamma 3 ends. So I'm going to call that the union of those two paths. So here gamma 3 is going to be defined as just t plus 0. So really just t is t goes from 0 to 1. And then gamma 4 of t, I should write gamma 4 of t. Gamma 4 of t is going to be 1 plus it. Again, as t goes from 0 to 1. Notice that t goes from 0 to 1 in all of these parameterizations. That's just a matter of convenience, actually. And so let's calculate these integrals now, and let's see how this works out. So the first one is, let's calculate the integral of f. So remember, our f is z squared. So this is the integral of f over gamma 1. So that's the integral of f of z dz over gamma 1. And remember that this is defined as, let's see if I can fit this on here. This is defined as, the line integral is defined as the integral from a to b. In our case, a and b are 0 and 1. That happens to be true for all of the curves. But it's going to be the integral from a to b, f of gamma of t, gamma prime. And so what we're going to do is we're going to integrate from 0 to 1. We're going to have gamma is t plus it. F of gamma is then going to be that quantity squared, because our function is just f of z is z squared, times gamma prime. And so if we differentiate gamma 1, what we're going to get is 1 plus 1i. So that happens to just be 1 plus I dt. And now this becomes basically a calc 1 problem, except the constants that you're bringing out of the integral happen to be complex numbers, and that's fine. So it turns out, let's see, if you square this, what's going to happen? We're going to get the integral from 0 to 1 is, here's one way that we could do this. This is going to be t squared times 1 plus I squared times 1 plus I, because we factored out the t from the beginning. And I know that 1 plus I squared is 2i. So this is going to be 2i times 1 plus I, whatever that is, times the integral of t squared from 0 to 1, which is 1/3. So this is going to be 2i times 1 plus I times 1/3. So altogether, I'd rather write this in the form a plus bi, or a plus ib. So this is going to be, let's see, 2i times 1/3, and then 2i times I is minus 2 times 1/3 will be minus 2/3. Okay, that's fine. We can leave it like that. Okay, so it's negative 2/3 plus 2/3 I. So that's the first integral. And then let's do this again for the second and the third integral. So for gamma 2, we again had t plus it squared. So the integral of f over gamma 2, and again, there's lots of different ways to write it, but let's write it as the integral of, say, z squared dz over gamma 2 is going to be the same. It's going to be the integral from 0 to 1, because those are the bounds for our parameterization. Our path gamma 2 was t plus I t squared. When we plug that in for z, we get that, whatever that is, squared times the derivative of gamma, which is 1 plus 2it. And now we have the job of squaring. We don't really have much choice other than just to walk through the algebra here. If we square t plus it squared, what we're going to get is t squared plus 2it cubed minus t to the 4th. That's all times 1 plus 2it. And now if we distribute, we're going to end up with, let's see, we'll end up with 1t squared plus 2it cubed minus t to the 4th. So that's all the stuff times 1, plus the stuff in the first parentheses times 2it. So that's going to be 2it cubed. So 2it cubed plus 4i squared t to the 4th minus 2it to the fifth dt. And then finally, let's combine, and then we're almost there. So we have t squared. We have 2it cubed plus 2it cubed is 4it cubed. We have t to the fourth, so negative 2 to the fourth plus, this should be 2i squared. Sorry, I didn't write that. 2i squared t to the fourth. So that's negative t to the fourth minus 4t to the fourth is minus 5t to the fourth. And so let's see what we've done so far. So that's the squareds, the cubes, the fourth powers, and then finally the fifth power is minus 2it to the fifth dt. And then we're integrating from 0 to 1, so this is going to end up being 1/3 plus 4i over 4. So the integral of t cubed from 0 to 1 is 1/4. So we get 4i times 1/4, so it's just I, minus 1, minus 1/3. Okay, so when we integrate all that, that's what we get. And this happens to work out to be the same, I'm sorry, minus 1/3 I forgot the I on the last one. And so this happens to work out to be the same negative 2/3 plus 2i over, not plus or minus, that's wrong, plus 2i over 3. Okay, so we get negative 2/3 plus 2i over 3, which happens to be the same value that we got before. Okay, so that's worth noting. And finally, we'll integrate over this third path, which we called gamma, this third path, which we called gamma naught. So gamma naught was gamma 3 union gamma 4. And it turns out, and I'll write this in some detail soon, but it turns out that this happens to be the integral over gamma 3 plus the integral over gamma 4. So what makes that, what allows that to be true is that gamma 3 and gamma 4 are, so gamma naught is a piecewise continuous, piecewise smooth path. And gamma 4 starts where gamma 3 ends. So you don't have to jump, you don't have anything interesting there happening. So it's just going to be the sum of those two integrals. And so for gamma 3, our curve was t plus 0i. So that's going to be the integral from 0 to 1 of t plus 0i squared times the derivative, which is 1. For gamma 4, this was the curve 1 plus it. So it's 1 plus it squared times the derivative would be 0 plus 1i dt. And so this is going to work out to be, this first one's just the integral of t squared from 0 to 1, so it's 1/3. The second quantity, let's see if we square 1 plus I, and we can bring the I out if we like, but if we square 1 plus I, we're going to end up with 1 plus 2it minus t squared dt. So this is going to end up being 1/3 plus I times, let's see, if we integrate 1 from 0 to 1, that's 1. Integrate 2it squared from 0 to 1, that's going to be just I. So plus I, because it's 2I over 2. And then minus t squared, so it'll be minus 1/3. That's all times I, so this works out to 1/3. Plus I minus I, so plus I squared, so minus 1, and then minus I over 3. And lo and behold, as you might have already guessed, this is the same negative 2/3 plus 2I over 3. So a natural question presents itself. If we integrate this function over any curve from 0 to 1 plus I, will we get the same value? Does it matter what the curve is? Does it matter anything about the function itself? So is this true for all functions? Is this true for all curves as long as I have the same starting and ending point? It turns out no. That's a little bit too much to hope for. And what the book does is the book actually uses these three same paths. But if you integrate z conjugate squared over these three paths, so over gamma 1, gamma 2, and then what I called gamma naught, which was the union, it turns out that you're going to get different values depending on what the function is. And so I think a natural question, which we'll leave unanswered for now, just a slight cliffhanger, is to figure out when will these functions always integrate to the same value regardless of path. And we're going to call that property path independence of the integral. So when are these integrals going to be path independent? And so the answer, stay tuned. We'll talk about that in some upcoming videos.